called it earlier. So why to bother about them? Anyone? Anyone wants to share their opinion about why do you think it's important to learn the concepts or the maths behind anything, or like, okay, anyone? I can.
Which process?
I'm so sorry, I can't hear you properly. Yeah, if you don't mind, you can put in the chat box also if your answers.
Good morning, sir, and classmates. Vikta, Sarvesh, Barnali, and I are members of the board who will present answers on the topic renewal process. So, first we will understand what the renewal process is. So,
Yeah. Okay, so some people have answered might help in deciding if the algo will be used in a particular scenario. Yes. So correct. So basically, if you have a hold of not just the maths or the concept behind the concept, why do you have certain kind of assumptions? Yes, certainly somebody has answered we know the concept well and we can able to create algo. Yes, it can be a very well it can be the first step to create an algo of your own in case you want to do something. So and basically selecting the right kind of algorithm, right kind of training time, how much training time will be required, what will be the model complexity, and what should be the parameter settings, right confidence intervals, right? All this understanding definitely aids or helps in better understanding of concepts and intuitively applying these in real life scenarios as and when required, right? When to apply linear regression, in what kind of use cases, right? And most important question is when not to apply certain things or when not to use certain concepts, right? So these internals or these concepts, I keep calling it concept behind the concepts because for concepts, everybody, most of us in the field of data science will be aware of concepts, but the concept behind the concepts should be, sorry, one second. Let me know if the screen is again visible properly. Yeah. Right. So concept behind the concepts, or the internals matter actually in helping us understand any algo, right? So great answers. I've got many answers on the chat window. And just give me 1 second. I need to. Yeah. So in today's agenda will be this. So we'll be going through a business case of which kind of cases or which kind of business problems linear regression is used in industry, and what are the limitations, what are the basically assumptions, or what is linear regression first of all, and what are the basic assumptions of linear regression, and like you have because linear regression is a mathematical rigid model, right? So it definitely has some assumptions that we need to follow in order to implement linear regression right? And there are many kind of techniques or algorithms for implementing linear regression. So one of them is OLS, ordinary least square regression, and there are many other kind of algorithms also, like stochastic gradient, kernel descent algorithms, right? But in today's workshop, we'll be specifically talking about OLS, ordinary least square regression, and how it works, right? What is the cost function of it, right? And during all these topics, we'll be more focused around what happens in the background, right? What is the mathematical concept behind anything, right? And then we'll gradually move to how do you measure the goodness of your algorithm or the model, basically. So using sum of squared errors, what is sum of squared errors, what is sum of squared total, and what is the relationship between all this, right? And then we'll see like how do you measure whether your model performance is good as expected or not. So using certain metrics called as R squared, adjusted R squared. So I'm sure whoever has like heard about linear regression, or so they would have heard about R square or adjusted R square for sure, right? So we'll just we'll cover R square, adjusted R square also in this in the upcoming slides. Then we'll also move to feature scaling. What is feature scaling? Why do we require features to be scaled? What effect does it have practically? We'll be going through a demo. Practically, we'll be seeing whether what happens when we scale data versus what happens when we don't scale the data in case of a linear regression use case, right? And the most important thing, so model interpretability. Model interpretability is such an important aspect. So in almost all the big organizations, or especially those who are like 120 years old or 100 years old organization, they require models to be implemented in such a way that they are like most interpretable, right? So that's why you would have seen or realized that in most of the organizations, deep learning or AI, so more than that, linear regression or the mathematical models are preferred as compared to the other deep learning models, right? And then we'll move to concept blue. So best linear unbiased estimates. So why is the OLS estimator called as blue estimator? What makes it blue? So, and then if we have some time left, then so as I said earlier, 3 hours time span to cover linear regression is a short time span. But yeah, we'll still try to cover regularization, at least touch base the concepts if we have time at all, right? So this is today's agenda. Anybody has any questions, please feel free to put it in the chat box or just like raise your hand. Just stop me. I'll just take a pause of 1 minute to see if there are any questions. Good.
Hello, ma'am.
Yeah.
Yeah, this is Akash. So,
Hi, Akash.
in 10th point, for model interpretability, like, do we have any special libraries for understanding how our model is working?
No. So in this section, we'll be focusing on model interpretability or the model summary, which we get from linear regression, and interpreting that summary is what we aim to like showcase here in the 10th point.
Yes.
Yeah, but you have, because we don't actually have, you have multiple libraries or in Python where we can definitely interpret model in a better way. But then again, as I mentioned earlier, the time we have got in our hand is 3 hours. But yeah, so
yes, ma'am. Yes, ma'am. I just wanted to know like whether there are any libraries to do it.
Yes.
Thank you, ma'am.
We'll go through them once we go to that particular section. We'll just definitely talk about them.
Okay.
Thanks, Akash. Argadeep, what's linear regression means? Okay, now we'll move to the next slide. So somebody has asked, Argadeep, am I pronouncing your name correctly? So Argadeep has asked what is linear regression. Yes, Argadeep. So just give me 5 minutes, then we'll move to exactly what is linear regression. So this whole session is all about that. Okay. Okay. So before, so in what kind of cases or what kind of use cases or real life challenges would linear regression be apt to use, right? So one such example is on the slide. So let's say you have a medical, you need to predict medical insurance claim for people, right? So what kind of input variables do you think, or what kind of data do you think, or what kind of variables would any insurance company be using in order to predict or estimate the medical insurance claim for people? Any answers? Any variables that you could think of? Just to for an example, I can say, okay, age of a person, the BMI of a person, the number of past historical medical data, and also any current diseases or past patient data, right? So these will be the major data that will be used. But you can obviously think of variables revolving around this, right? Like past medical claim, number of diseases in past, severity of disease in the past, right? Or past patient data, past medical claim, and other variables that might influence or that might affect the medical insurance claim. Like how many number of dependents do you have in the family? What is your source of income? What is the So any kind of suggestions you guys have for the variables that might be used or that can be used for this problem? Anyone? Let's make this session very interactive or two-way, right? So because this is what we aim to achieve basically, because if it's just a one-way talking, then doesn't really help, right? Not you, not us.
Along with the age and BMI, income of the person, and whether he is male or female.
Exactly.
Gender.
Yes, definitely. That's good. Yes. Okay. So anyways, so this is one of the, so now you see, what are we predicting here? We are predicting medical insurance claim. It's a numerical variable, right? I'm sure numerical is a variable that can be added, subtracted, right? You can do all mathematical operations. So this is a number that we are going to predict using linear regression. So you see all those use cases where our dependent variable, as we call it, or the variable which we need to predict, right? That when when that variable is a number, we go for linear regression. It can only be used when your dependent or when your variable that you need to predict is a number, is a numerical variable, right? So insurance claim is it will be in dollars, in rupees, in any currency, right? So, but obviously it's a number. So this is an example of where in real life scenario we can use linear regression. Any more examples? Anyone would like to code for where to use linear regression? Where should we use linear regression? Any business case, small, big, anything.
Ma'am, in ice cream factories also, they can predict the ice creams that they daily need in summers and in winters. They can also use linear regression for that.
Exactly.
And in banking sector, like how much loan should we give to the person based on his characteristics?
Exactly, correct. That's
house price prediction.
Yes, house price prediction has been a very
in real estate.
Famous, very famous example or use case of linear regression. Mahima said sales and marketing. Yes, Mahima, sales and marketing, we can have multiple use cases, definitely. Okay, yes, so I guess everybody knows now like what kind of business problems we can use this linear regression for, right? Now, let's move to more specifically linear regression internals, or the introduction to linear. So I think many people were asking what is linear regression, when do we use it? So when do we use this is that first question that we answered. In what cases when we can leverage linear regression? Now, to answer the question Deepa asked, or a few more people pinged us. So what is linear regression? So I'm sure like whoever has tried linear regression in the past or heard about them, it might be knowing. So it is basically to establish the fact that there is a relationship between the dependent and the independent variables. Now, what is dependent? So in our in our medical claim prediction example, The medical claim is the Y variable because it is dependent on other variables, which like age, BMI, income, all those variables that you guys told. So since medical claim is dependent on those variables, so medical claim will be now called as Y variable or dependent or response variable, right? Different names for that same, or Y variable. Now, the other variables on which the Y is dependent, so those are called as independent or predictors or X variables, right? Okay. Now, Y is, we assume that, so basically the base of linear regression is a mathematical model. So Y equals to f of x, x1, x2, x3. There can be one or many independent variables here, right? Now, people might wonder. So some people, some of you might already have would have heard about terms like covariance, correlation, right? So if we already have something called as correlation that establishes the relation between x and y. So why go for linear regression? Anybody?
Yes, ma'am, because linear regression would tell us a mathematical relationship between the variables and correlation won't tell us, I guess.
Yes. So yes. Yeah.
Like if we have a strong positive correlation between the feature and the output, I mean, dependent variable. So how much it is changing with respect to the each feature. So change in unit value of one feature, how much it is affecting on the dependent variable.
Exactly.
We'll get it from correlation.
We'll get it from regression, sorry. So yeah, you get to quantify that effect. So let's say y equals to 2x. Now you can imagine x is performance and y is salary hike. So if y equals to 2x, you're quantifying that for every 2% increase in performance, you're getting 1 unit increase in salary hike. So you are basically able to quantify that relationship, right? So that is the importance of linear regression, right? Which you will not get by covariance or correlation, right? I hope, Agadeep, you got an idea of what is linear regression now?
Yes, ma'am.
Sure. Okay. Then nice to know that. Okay. So as we already talked about those terms, covariance and correlation, we'll just try to quickly cover that also in this way. So covariance is a measure of how one variable changes with respect to the other, right? So in the formula, you can see, basically it's xi minus x bar, right? So one particular value, how much it is deviated from the mean of that particular variable itself, right? So in generic terms, we'll say, okay, this is like 2% varied from mean. So same way, so it kind of measures if if one variable is related with the other variable, or how it just measures the direction. So if one is increasing, let's say stock market, let's take an example of stock market. If stock A is increasing and stock B is also increasing at the same time, so covariance will give you that indication, that direction, sense of direction, right? So if it is greater than 0, the variables move together. That means they have a positive covariance. So like if stock A increases, stock B increases. If stock A decreases, then stock B decreases. If it is less than 0, then the two variables are extremely opposite in nature, right? Like if stock A increases, stock B decreases, right? And vice versa. And if it is 0, if the value of covariance is 0, then they are two independent entities. So stock A, whether it increases, it decreases, doesn't affect stock B, right? So that is that sense of direction, how two variables are behaving with respect to each other, right? That we get from covariance. Whereas in correlation, you measure the degree of relationship. Basically, you get not just the direction, but a magnitude of change, right? You see the formula. It's basically covariance divided by standard deviation of x and y. So, yes, anybody? Okay. So basically, this is like, so you're basically cancelling out the units because it's present in the numerator as well as the denominator as well. So this correlation becomes unitless, right? Most importantly. And then it becomes scaled version because you're dividing by standard deviation. So this range will always be between -1 to 1. Unlike covariance, covariance can range from -infinity to +infinity, right? But this particular formula of correlation that will always give you values between -1 to +1. Now, what is -1? Again, same negative correlation, +1 perfect correlation of positive correlation, and 0 meaning independent of each other, right? Intuition is same as covariance, but then the magnitude obviously is the extra thing that you get in correlation. Now, just one more thing. Have you ever imagined, like if you see the denominator here, it's n-1. Why is it n-1 and why is it not n? You'll have, obviously, you see the summation is from I equals to 1 to n. But then why in the denominator we have something called as n-1? Why are we not taking the mean of entire thing? Anyone?
Don't know, ma'am, but I was about to ask that same question. Like, why it is n-1?
Ma'am, we won't take the correlation with the same object, same feature.
Okay. Okay. So let's see, if you, let's imagine, this is because of degrees of freedom, n-1 degrees of freedom you have. Now, there is a concept called as sample. There is a concept called as population. Population is the entire universe. So if you, let's say you wanted to prove a statement that average height of all the boys or between the age of 13 to 20 in India is 160 centimeters, something. I'm just taking random example, 170 centimeter maybe, right? Now, to prove that statement, you will not be able to gather entire India's all the boys data that belong to the age range of 13 to 20. You'll always have a sample, right? You'll not have a complete population, and that happens exactly in the real world challenges. You'll never have population in hand. You always have, you basis the characteristics of the, yeah. Yourself. Oh, thank you. Yeah. So basis the sample, you will be supposed to estimate something about the population, correct? So you do experiments on sample, but you draw out inferences about population, correct? So population, just try to remember, it is a big, or the entire data, but always at your hand, you'll have a sample of data, correct? So now, why degrees, coming back to the degrees of freedom now. What happens, let's take an example. You have 10 rupees, let's say now, in your hand, and you want to spend it only on 4 items only. Let's say you bought first item for 2 rupees, second item for 2 rupees, and then third item for 3 rupees. So 2 to 4 and 7 rupees you spent now on 3 items. Now you know that you have only 10 rupees in your hand now, but you were free to choose the amount that you spend on the first 3 items that you bought, right? Like you could have bought the item number 1 for 4 rupees and item number 2 for 1 rupee also. But basically you're free to choose or spend the amount until n-1, 4 minus 1, that is 3 items, right? You can buy. Now, once you have bought those 3 items, let's say you spent in a total of 7 rupees. Now, the 4th item is you are bound to spend only rupees 3 for the 4th item. So n-1 terms are free to move in order to maintain a constant mean or constant sum, right? So that is called as degrees of freedom concept, right? So always when the number of terms are n, you will always have n-1 terms which are like free to move or free to, given a constant variance or constant mean or constant sum that you want to achieve using those terms. Hope that clarifies. Any questions?
Yes, ma'am. Yes, ma'am. This is only applied for a sample, right?
Yes. Because we always leave that slightest uncertainty because so that because we know the population mean always, right? So we try
Yes,
to we try to balance the terms in such a way that the mean remains same, but then we'll be like making makeshift around the n terms. The terms basically we can so just take the example of that 10 rupees spend which I told.
Yes,
right?
ma'am. Clear, ma'am.
Yeah. Okay. One more very important concept, that correlation is not causation. Anybody who has heard about this this phrase in the past? Anybody? Feel free to talk. Like even. Okay. So what is the statement or the phrase giving you an idea of correlation and causation?
Ma'am, sometimes correlation can be spurious also. Like for example, if a tree is growing and the stock market is growing, there may come, the covariance may come to be positive, but that doesn't mean that they really have some correlation among them.
Mahima gave an excellent example of correlation and is not causation. Yeah. So basically, so for correlation, you have a formula. So I'll just steal this example from Mahima. So basically, if she said in stock market, stock A is growing, and same time a tree is also growing. So does it mean that tree growing depends on stock market increase, or the vice versa? Does it mean like that? Just another example. So let's say you have summers and ice cream sales are increasing now, but does it mean like only summers cause increase in ice cream sales? No, because there will be some effect of some kind of lurking variables or mediator variables, right? Maybe the people are eating more ice cream in that very local area only where you are selling the ice cream, just because they sweat more in that area. So that count of people sweating, right? That is a mediator variable. So there exists a mediator variable which can basically be responsible for the correlation between those two items. So like ice cream sales and the summer, right? But that doesn't mean that is causing that, correct? So again, taking the tree and the stock example. So there might be some hidden or other lurking variables that might be responsible. So it doesn't mean like if tree size is increasing, stock is also increasing. So that doesn't prove a causation there, right? So for causation, we always need to rule out those lurking variables or mediator variables, correct? And there is an entire concept of causal theory. So you can like maybe Google about it. So causal inference is entirely different science, but yeah, correlation is definitely not causation until unless we have some certain kind of mathematical evidence around the causal. Okay. And one more example is just on the screen. So people in India spend more time spend more in the shops when it's cold and less when it's hot. So it doesn't mean that cold weather causes frenzied high street spending, right? Because it doesn't establishes the fact that cold weather is causing people to emotionally go and spend out there, right? So it is not establishing that fact, although they are correlated with each other. Okay, so now next thing is types of linear regression. So basically there are only two types of to be very simple, there are only two types of regression, simple and multiple. From the name itself, the name itself are very intuitive. Simple is just one independent variable, one dependent variable. So y equals to mx plus c. This is what you get as an equation of a line, right, for linear regression. So here, if you write y equals to mx plus c, only one variable, which is if mx, okay, so only one variable here, that is x, right? So that is called a simple linear regression. In case of a multiple linear regression, you will have multiple variables like y equals to mx1 plus beta cx2 plus and so on, right? Plus an error term. Now, so you see, so in simple linear regression, you'll have always the equation of a line, right? Whereas in case of multiple regression, you will have equation of a plane, because you cannot represent just more than two variables in the form of line in 2D plane, right? You will always have to have a vector space, right? Or a hyperplane that will define your model in case of multiple linear regression, unlike simple linear regression, correct? So as I already told, so beta naught is the intercept term. So let's just interpret this equation. So this is what you will get as your mathematical model. This is the model. This is linear regression model, right? For a simple linear regression. Y is dependent variable, x is independent, beta 1 is the regression coefficient of x, meaning, again, if you remember that example, y equals to 2x. So by how much quantity change in x will affect 1 unit change in y, right? So that is represented by beta 1. Now beta 1 is slope of this line, right? So in high school maths, we would have all of us have studied this, right? Y equals to mx plus c. X represents the m represents the slope. So same m has been replaced here by beta 1, and there's a constant or intercept. So if we want to start this line from origin, right? If we want to start this line from origin like this, so then there will be no beta naught, right? So this term will go away. Yes, there will be no beta naught. But now, as you are introducing an intercept term, you will have this portion as beta naught. So how much away from origin is your line, right? So that is that is beta naught, right? And always see, let's say this is your actual point. These gray points are your actual point, and you are trying to fit a line, a regression, basically regression model, a line to best estimate these points, right? So there will be always some kind of error that you will be having, right? Because see, for this gray point, consider that you predicted this point, right? This point on the line. So this portion will be the error, right? So that is referred by epsilon, or the error of the estimate, correct? Just let me clear. Yeah. Now, so one more important thing. So since I was telling, so linear regression is a mathematical rigid model. So once you have the data in the x variables, and you do all the calculations, do all the mathematics, create the model for linear regression, then you can basically get rid of those points, right? You don't necessarily need to hold those points, because anytime the next new or the next x variable will come, you can fit that x, you can fit that value in this x variable, and you'll get the corresponding y. You don't actually need to store the data points. So that's why linear regression is a kind of mathematical rigid model, right? Okay. Any questions till here? Any doubts, anything you want to express? Or you can, I'll just open the chat in case anyone. Yeah.
Sir, ma'am?
Yes.
Is it necessary that the best fit line should passes through the origin?
No, it's not at all
not
necessary.
Passes through the origin.
No, it's not at all necessary. The best fit line will be decided just based on your x and y variables and the dependent. You can have just y equals to 2x also, right? It's not mandatory to have y equals to 2 plus 2x or 3 plus 2x, right?
Ma'am, if we have multiple data points, then the increase of error rate can be higher or can be same, ma'am.
I'm not sure I exactly got your question. So if in case we have the data, more data, you're saying?
Yes, ma'am. Yes, ma'am. More data points, ma'am.
And
then the error rate will be higher.
Like, why do you say that? Like, why should it be there? Like, excellent discussion point. Basically, we'll go through this discussion, this point again, while we talk about the assumptions of linear regression. But ideally, to what you said, right? So, in case we take more and more data, should we keep getting more and more error? Then nobody will tend to get more sample, right? Get more data sample, right? It shouldn't be the case,
yes.
ideally.
Yes,
correct?
ma'am. Like ma'am. Yes, ma'am.
Yeah. Okay. Any more questions? Any more points, discussions, comments? Is the error and residual same? Yes. They are the same terminologies. To handle outliers, Santosh,
Ma'am, so in this multiple linear regression, so the slope defines how much important that feature is it, ma'am?
Yes.
So the beta 1 and beta 2 are the importance of that feature in predicting y.
Correct.
Yeah. Okay.
Yeah. Any questions? Any more points? Chat window. What is outlier? Okay. Somebody asked what is outlier. Outlier is a let's say, okay. Let's say you all had a test. Okay. Out of 100, almost everybody scored 80, but there was one person who scored like 10, or there was one person who scored 100, basically, right? So it's kind of an outlier. So it doesn't fit. So most of you scored 80. So the person who scored 10 doesn't kind of fit in the overall distribution, right? The mode, basically, or the distribution where most of the records belong, right? So it's the entities which don't fit to the current distribution are called as outliers, right? And linear regression is susceptible to outliers. So you might need to take care of them before you perform any kind of linear regression modeling. Any more questions? Hope I answered that question, Mahesh.
No, madam.
Okay, no questions. Okay, so there are many applications of linear regression, right? We already talked about a few when we were talking about the business case. So basically, you can identify how much y is dependent on x, and with basically you can quantify, right? So with what change with percent, so with how many units of x change in x is causing 1 unit change in y, right? So and you can also achieve, like, you don't, if you're interested in point intervals, right? Like my this variable can belong from this range to that range, right? So that kind of feature estimate intervals also you can get from linear regression algorithm. Now moving to the most important part, that is assumptions of linear regression. Now, as I said earlier, linear regression is a mathematical rigid model, right? So you can get rid of all the points and you just have one equation of a line or a plane, right? That denotes your entire characteristic of the sample in hand, right? So obviously, when there is some mathematical model, you'll have some limitations or assumptions that you need to take care of in order to satisfy that or in order to implement that particular mathematical model or linear regression in this case. So first, so there are like major these 5 assumptions. So linearity, no endogeneity, normality, homoscedasticity, no autocorrelation, no multicollinearity. So before we'll go through them one by one in detail, but before we go there, anybody has any idea of any of these? and why is it important? Like, why should we even bother about linear regression? So in practice, generally, nobody even cares about these assumptions, but these assumptions play the most important role in linear regression, or in execution, or in at least deciding whether we should go for linear regression at all or not. So many a times I've seen like people blindly just implement or execute linear regression, right? But that shouldn't be the case, because if one of them gets failed, right, you'll not be getting the or appropriate results of linear regression, right? Okay. Yeah.
So I think linearity is about like the model itself is about having a linear relationship between the independent and the dependent variable. So linearity should be satisfied, and normality is like to scale the features in the same range, so that maybe computation will be easier if you make it.
Okay. Yeah. Close.
Like all the features can be normally distributed.
Yeah. Okay. So this is regarding the error. Yeah, I'll go through it. But yes, the answers are very close. Nice. Thanks, Akash. Anyone else also wants to? I'll just look out for the chat.
Hello.
Yes, Apurva.
Hi. Yeah. So no autocorrelation means the dependent variables that we have, if they are correlated amongst themselves, so there is no need for so they are pretty self predictive.
Exactly. Yeah, the same happens with the errors also. Right. Yeah. The concept is same, whatever you told, the same thing, but it applies to errors here. Okay. So thanks for the answers. So I'll just move to these concepts one by one, right? So linearity, as Akash said, so all the variables independent, basically the x and y, each of the x, so x1, x2, x3, let's say you have 3 variables in your model, 3 independent variables. So you should always have a linear relationship between the x and y variable, correct? And how can you prove that, or how can you see that or verify that? You can simply plot a graph, a scatter plot, maybe the best one to see the linear relationship. So you can plot a scatter plot between the y variable and the x1 and x2 and x3 separately. In case you have 3 variables, you can go ahead making 3 plots, right? So that will make you see like what is the relationship between x and y variable, right? And so basically what happens in case you don't have linear dependence between x and y variable? Will you be able to apply linear regression in such a case? Anyone? No, because in that case, your basic assumption, yes, Mahima. So will you be able to apply linear regression when you don't have linear relationship between x and y?
Yes, ma'am. Maybe we can transform
Exactly.
that relationship into a linear, and then can apply the linear relationship.
Exactly.
Linear regression.
Yeah. So that's what. So either if you tried your best, if you see that there is no case where your x and y can be linearly related, then obviously you'll have to go for nonlinear regression or nonlinear methods of estimating or predicting, right? But if you can see, like, you can go ahead with exponential or logistic transform, right? Log of x, right? And in that, if you see that if your variable now becomes linearly dependent between x and y, there is a linear relationship between x and y. So then you can go ahead and again do a linear relation. So if you go ahead and see log x. So y log x. So see, it's like, okay, we are able to see this portion. See, the log x graphs goes like this. So so if your data is has lot many values and x, but it has pretty consistent or specific range of values for y for any kind of x, right? So kind of you narrow down the band and make it under fit for linear regression, right? Using exponential or logarithm, right? So exponential and logarithm are just mirror images, right? Mirror images as in, this is like E of x, this is log of x, correct? So these all things you can let you decide whether you can go ahead with linear regression or not, or whether the first important assumption holds true or not, right? So you can check it using graphs or plots, right? Or you can, if you feel there is a linear dependency or linear relationship between x and y, then only go ahead with the linear regression. Otherwise, if you see that there is no linear relationship, you can transform the variables using log or exponential transformations. And still, if you're not able to achieve a linearity between x and y variables, then you obviously need to go ahead with a non-linear regression technique. Okay. Second assumption, or no endogeneity.
Ma'am.
Right? Yes, Devansh.
Ma'am, I have a doubt in linearity concept. So as you said that if we have more than 3 independent variables, and suppose that 2 of them are linearly related with that dependent variable y, and one is not related.
Yes.
Linearly. So in that case, should we apply linear regression, or we will do a transformation?
No, so then you should do the transformation only for that particular variable, right? Which is not showing you enough linearity as of now, right?
Okay, ma'am. Thank you.
Thanks.
Ma'am?
Okay. Yes, Himanshu.
Ma'am, if we change the, if we transform one feature and other features are not changed, then it is not like the distribution of that feature change, and it will affect the relationship between the features and the independent variable.
No, basically, when you're talking about relationship, so let's say now, how will you interpret the coefficients? So, since you change only, so you didn't change x1 and x2, so it will be like y1 equals to 2 of x1 plus 3 of x2. So 3 units of change of x2 results in 1 unit change in x1. But in case of x3, since you transformed it to log or exponential, so then let's say log. So log of 2 of x3 something happened, 2 of x3 equals to y1. So now you'll have to basically take the exponential. So do the math there. So exponential of y equals to now x3, right? So 1 unit of x3 will result in a different kind of change in y. So it's the interpretability that you will have to accordingly assess.
Okay, ma'am.
You got it?
Yes, ma'am.
Okay. Any more questions? Okay, I'll assume that is no. No endogeneity. Okay, this is the second assumption that we were talking about. So basically, what does endogeneity mean? There should be no relation or between the variables, the x variables I'm talking about, and the error terms, right? So whenever, as I was mentioning earlier, whenever you build a mathematical model, you'll always tend to have some error because this is a rigid model. It's a straight line or a straight plane. It cannot go like curves and all. So you'll always have some error here. So that error terms and these independent variables should not be dependent, or there should not be a link between them, right? Why? Because it leads to a case of called as omitted variable bias, right? And so now what is omitted variable bias? Let's say you have y equals to a plus bx plus cz plus u, right? You have this equation of your y variable. ABC are the parameters or the coefficients. A is the intercept, B is the coefficient for x, C is the coefficient for z, U is the error term. Okay. Now you can see there are only 2 independent variables here called as x and z, right? You can relate this this equation by y equals to beta naught. 1 second. So this term can be beta naught, and this term can be x1. This can be x2, right? And this will be the coefficients. Beta c are the coefficients. Beta 1, beta 2, right? So now this equation is of that linear regression. Now, let's say you want to omit or you want to get rid of the variable z from this equation, but there exists a relation between z and x in such a way that you have z equals to d plus f of x plus some error term, right? So now substituting the value of z from here into this equation, right, you will get this final equation. Now, what I said, like, since you see there is some kind of dependency between the independent variables itself, so z is kind of dependent on x, you are not able to get exact or true coefficient of x here. You are getting b plus cf. But in the original equation, what was the coefficient of x? B. Now this cf got extra added. So it's now no longer now the true representative of coefficient of x. It has some extra terms. So this also happens again in case of multicollinearity when you have dependent variables, independent variables themselves correlated amongst each other, right? So this is a problem for linear regression. Now, 1 second, I'll just close this one. Third assumption. Third assumption is normality and homoscedasticity. Most important ones, right? Why is it so? Why? What is normality? Anyone? And I'm talking about error terms here. So normality and homoscedasticity of error terms are the most important conditions for or assumptions for linear regression. What is normality? Anyone would like to pitch it?
Ma'am, normality means the error terms are normally distributed with mean 0 and variance sigma square.
Exactly. So in this case, linear regression, we always have to assume that error term, the epsilons we were talking, y equals to mx plus epsilon, right? Or e, whatever notation you want to give it as. So error term should always be normally distributed, right? Otherwise, it will always be difficult to estimate or quantify or establish a linear relationship model, execute a linear relationship model, right? And if it is not normally distributed, then you can, how can it become normally distributed? So you would have heard about central limit theorem. Anyone who remembers central limit theorem from high school maths or
when the sample size increases, the data becomes normally distributed.
Exactly, right? So if you take an example of a throw of a dice, right? Let's say, when do you get a sum of 1? When do you get a sum of 2, right? So if you just throw dice only once, everything will be 1/6 probability. But when you kind of throw 2 dice, 3 dice, 4 dice, the probability of getting the sum as 1 and the probability of getting a sum as 2, the probability of getting a sum of 3, and so on, all that becomes a normal distribution, right? So like now probability of getting a sum as 2, getting a sum as 3, getting a sum as 4, like that, like this, it will keep on becoming if you take enough samples, or if you for example, like if you throw a dice multiple times, you tend to get this kind of distribution if you are considering the sum of these numbers, right? You threw your dice once, you got a sum of 1. How many ways you will get a sum of die equals to 1? There is only one way, right? In case you throw the dice only once. But in case you throw the dice twice or thrice or like multiple times, this will kind of become a different number, right? So if in case your data is not normal, taking more and more samples, so we call that called as bootstrapping, right? Bootstrap aggregating, bootstrapping. Basically, bootstrapping is, let's say you have a bag and you have some like 100 balls inside it, right? Now of different colors. Okay. Now when you are asked, all of you are asked and to pick a ball and note down its number and then put it back inside the bag, right? So this is kind of data collection you are doing, kind of basically. If you are having a less number of sample, you can just do bootstrapping. You can kind of repeat the sampling process, and then you can make this error term normal, or the distribution of the error term normal, right? Now, zero mean of the error term, right? So errors should be zero mean, like E of error term, expectation of the error term should be equal to zero, right? And there should be always constant variance between error terms, right? So if you don't have a constant variance, so what will happen? So in case you you prepare one model, yeah, so you prepare one model. So in case of some data, you have different error terms. In case of other set of data, you have different error terms. So you will never be able to aptly assess or quantify your data, right? Quantify the behavior of your data, because every time the behavior of the error changes, it doesn't. It's no longer it's not having a constant variance or mean, right? So that means the behavior of the error terms is changing, which will never allow you to exactly or aptly or accurately build a linear regression model. So always there should be homoscedasticity, not heteroscedasticity. Homoscedasticity is good, hetero is bad. Just if you try to remember in that way, right? The size of the error should be same, approximately like constant variance, right? Constantly same, no matter what is the data that you're taking, no matter what is the size of the data you're taking, right? If they vary as per your data changes, then there is a problem. So always in a graph like this, right, when you plot the predicted values on the x-axis, sorry, there is it's missing here. So predicted values versus the errors. On the y-axis, you measure the errors. On the x-axis, you say predicted values, right? So first predicted value, it shows error like this. Second predicted values, it shows error. In case you get a shape of, one second, in case you get a shape of this kind of thing, you are getting a cone, right? Kind of cone. This is a problem. This shows heteroscedasticity in your data. It should be always constant. So if it would have been having some points here, right, more points here. So in case it would have been a linear thing, right, not a conical shape, then that means it has a constant variance. Obviously would have had one line only, right? Only one value. So that is called as homo or heteroscedasticity. If you have a conical shape, when you plot your coefficients, error terms versus the predicted values. So this is the predicted values, and this is the error term. Okay. Sorry for the writing. Okay. Now, but what can be the causes, right? Like what? So basically, you might have something called as omitted variable bias. Again, I said there will be two variables that are internally correlated with each other. There might be outliers, right? So let's say so that's why we initially I told, like, linear regression is susceptible to outliers. It does not behave properly when you have outliers in the data. So you need to scale or get rid of them or do some treatment for the outliers, right? Or the log transformation of any independent variable. If it's not very much scaled enough, it doesn't look proper, it does not have linearity with the y variable, then you would need to do all these things. You might need to take care of outliers. How can you treat outliers? You can basically confine them. You can standardize the whole feature, that particular feature which has outliers, right? So that it values ranges from 0 to 1. There are multiple methods, right, to take care of outliers. Correct? Now, how do you detect? So this is normality and homoscedasticity that we were talking about. How do you test in programs, right? Like when you write Python program for linear regression, then how will you identify that there is heteroscedasticity. Okay, one method is obviously you can plot the predicted values versus the errors. Now, but if you had to quantify, right? So how will you do that? So there exists a test called as Bruch-Pagan test. Right now, how does it work? Basically, you first fit a model between independent variables and dependent variables, x and y's, right? Sorry, x's and y. There will be only one y here. And then calculate the residual of the model. Residual and error is the same. The third step is you fit a entire new regression model. Now this time, only this time, what will be your y variable? The errors which you got from the first step, the first one, or the second step basically. The errors that you got from the second step, that will become your new response variables. Now, again, you will get a new R square, right? The goodness of fit of your model. Now, what you calculate a term called as chi-square test statistic, which is number of the observations, the number of rows in your data into the R square new. New meaning the R square which you got when you took response variables as error terms as a responsible variable, or the squared residuals, right? That. And this will give you a number, correct? N into R square nu. Now, if you take the p-value of that, p-value as of now, we can just treat it as probability of that value coming from the normal distribution is as extreme as this one, right? So let's say if you get lower the p-value, better the, so more is your hypothesis, or basically better the p-value, more is the importance of that particular thing or variable, right? Or the statement that you are going to prove, right? Or so if the p-value is less than some threshold, mostly the acceptable market threshold is 0.05 basis the experiments that have been performed, right? So in 95%, so 0.05 is the threshold that has been decided. But obviously it's not like hard and fast rule. You can change this basis on your business case, right? It always depends on your business case or the use case that you're dealing with. So if, let's say for now, if we just take 0.05 as the threshold or the alpha value, then if the p-value is lesser than 0.05, we'll say, okay, we are 95% confident that this is, we reject the null hypothesis then, right? And then conclude that heteroscedasticity is present. Why? Because in this Bruch-Pagan test, the H naught or the null hypothesis is there is homoscedasticity, and the alternate hypothesis is there is heteroscedasticity. Correct? So this is, you don't, when you will do this Bruch-Pagan test on Python, you will not need to go through all these calculations manually, right? There will be one library, there will be one test.bp test, from where you will just invoke that function, and then you will just pass on your data inside that, and then you will get the value, p-value. If it is less than 0.05, you say, okay, homoscedasticity is there, then we are good to go for linear regression. If it is the p-value or the probability that it throws, it's greater than 0.05, it's greater than 0.05, yes. Then you say, oh, my model has heteroscedasticity. I need to treat that first, and then only we can perform linear regression, right? But this is the way internally it works, okay? Now, any questions still here, so that I can just move to the next two assumptions also. There are two more left.
Ma'am, that normality assumption, it is only for error term, or is there any rule like every feature should be normally distributed?
No, this is just for error term. In terms of assumptions in linear, this is for error term.
So like the feature can be normally distributed, or distribution can be in any manner? Right?
Yes, yeah, but obviously you will, once you make, you say that you saw like x1 is not normally distributed, you went ahead and made a model. Now you saw like you're not getting enough accuracy or enough goodness of fit, right, as expected. Then you might need to go ahead and maybe make that variable normal, or depending on, again, as per your use case.
To make that normal, we will normalize or standardize the feature.
Exactly.
So then it will become, yes.
Yes.
Yeah. Yes. Okay.
Standardize the feature. Then it will become normal.
Yes. Okay.
Okay. Any more questions, and then we'll before we go to the next assumption. I'll just look at the chat window. Any more questions? Any doubts, questions, clarifications that anyone has before we go on to the next assumption? Okay.
Ma'am?
Yes, Akash.
One more question, like if we are dealing with data that is related to some time series data, like stock price prediction, like then also these assumptions will be carried out.
No, these assumptions are strictly for linear regression, not for time series. Time series, you should have autocorrelation, right? So because there you have only one variable, right? So time series is a very interesting concept. Like maybe once you get time, you could go ahead to the Algoritmo Labs Instagram channels or LinkedIn, and you can read about these short assumptions and about various kind of techniques that you have for time series or assumptions for time series, right? So
time series will have some different assumptions, like
yes.
Okay.
Every algorithm has different assumptions, might match here and there, but yeah, these assumptions which we are talking about strictly are applicable for linear regression.
Okay.
Any more questions? Any doubts, comments? Is it too slow, too fast, anything? Okay, I'll treat it as no, so no questions. So then we'll move to next assumption, which is no autocorrelation between the error terms, right? If you can imagine, like if you have autocorrelation, right? What is autocorrelation first? Like your next error term. So let's say you had 5 rows. The row number 2's error is dependent on row number 1's error term, right? So it's like your error terms are interdependent on each other. There exists kind of autocorrelation between the, why auto? Because the same variable, right? Correlation means dependence, right? Some kind of dependency between those two. So if the error terms themselves are correlated between themselves, right? So always there will be no need of model, right? You can always, your mathematical model or your linear model will be clever enough to get that idea that, okay, if my next term is dependent on this previous term, then obviously you will be getting, your model will be too good to be true, right? Your model will have great accuracy or and large coefficients, right? For to be very specific, large coefficients, x1, x2 will be like, large coefficients, larger coefficients you'll get. Then you will think basically that, okay, now my x1 is really impacting y variable, but that is false view that has been given to you, right? Because of the error terms correlation present, right? So ideally, in order to get the true estimate of the coefficients, you should not have correlation between error terms while you do a linear regression, right? Also, in this case, right, when you have autocorrelation present, you will be more confident, right, about the predicted values, right? So rather than, so you'll say, okay, in a number line, let's say if you had a variable, if you were to give a variable's estimate, like the range where it can belong, right, on a number line. So let's say this is 5 and this is 10. So let's say when you don't have any autocorrelation between the error terms, you would have given a range, okay, my x1 can be in the range of 5 to 10. Now, once you have autocorrelation between error terms, you start getting more better fit, right? But that is not true fit. Although it will give you false views that you are achieving great accuracy and you are having more like better fit, right? And then you will have, in case of autocorrelation present, you will basically narrow down the the estimates, right, of your variable, of your y variable, right? Now you'll say, okay, I think it belongs from 7 to 9 rather than 5 to 10. So you're kind of narrowing down the band of this variable, right? Now let's imagine when you have unseen data. Now, so you will have test data feed into this model. Since you said, or your model decided my always my forecast will be between 7 to 9, right? You kind of narrowed down the gap. Now unseen data, you saw values again 10, 9.5, something like that. And this range, since you have already narrowed it down, you are more likely to get more errors in case you apply your model to predict for unseen data. So that is the major problem for in case of autocorrelation between the errors being present, right? Now, how do you detect that? How do you detect that autocorrelation presence? Using Durbin-Watson test. Now, what is Durbin-Watson? What does it do basically? Durbin-Watson is names of the people who designed this, but error term, what is this test used for? To prove the existence or non-existence of autocorrelation in your error terms. So how do you calculate? We take the sum of all the errors, current error minus previous error, ET minus ET minus 1, right? For each one, you will do this, right? ET minus ET minus 1, ET minus ET minus 1. And then you'll take a square of those terms and add all these summation, right? And then you will divide it by the summation of all the error terms square, right? You will get a number. Now, if this number is 0, then it represents, so basically, ideally, this number will always be between 0 to 4, right? So between 0 to 4, the mid value is 2. So basically, you can say, just try to remember in this way, like if you have 2, that if Durbin-Watson gives you 2, then there exists no autocorrelation. If it is lesser than 2, data is positively autocorrelated, errors are positively autocorrelated, and value of dw or d here, if it is greater than 2, that means data is negatively correlated, right? So when first error increases, second decreases, something like that, right? So this will be kind of for your quantification or getting the idea of autocorrelation, how much autocorrelation exists or what kind of autocorrelation exists between your error terms in your data. Okay. Any questions here for autocorrelation? Before we know.
Just like correlation, so autocorrelation is between error terms, and this lies between, is it like every time it should lie between only 0 to 4?
Yes, because basis this equation, it will always come between a value within the range of 0 to 4. Okay. But it should not lie. So ideally, it should say close to 2, right? To identify or to establish the fact that there is no autocorrelation. If it is like something other than 2, like 3.4 or some 1 point something, right? So that means there exists some autocorrelation.
Okay.
Okay, now comes the most important, or very important assumption of linear regression, that is multicollinearity. Before we just go into the nitty-gritty of multicollinearity, or what is it, how does it behave, anyone would like to express what do you understand by multicollinearity and why should it be not there in the model? Anyone?
I think multicollinearity is about like one feature is only explaining about other feature.
Exactly.
Like, yes, ma'am.
Okay. So can somebody relate it with some omitted variable bias? We just talked about that some slides back, right? Omitted variable bias. When one variable is itself correlated with each other. What will happen? Try the same equation, or
Yes, ma'am. So in this case, so like as one feature is only explaining, like one predictor variable is only explaining about other things, so the coefficients are also somewhat related.
Yes.
So we can't get, so in this case we can't get a perfect model, so we should eliminate one feature, I guess.
Oh, correct. So yeah, so I'm just trying to give you some ideas. How can multicollinearity affect? So first of all, what is multicollinearity? So when you have independent variables, one or more independent variables, right? Predictors or independent variables, right? And there exists some kind of relationship internally between them, then that causes the model to be unstable. You will not get the true coefficients or true reflections of your the quantification of x and y variables, right? so so like again, why I referred to this equation again, here you can see, so in this case z was kind of dependent on x, so ideally the coefficient of x is b, but since because of multicollinearity or maybe like some dependence here, you kind of x coefficient of x is no longer just b, it has some additional influence also, right? So this also happens in multicollinearity as well, right? So in case you have one or more variables internally correlated, so it will cause your variables your model not to be perfect. Now what happens, okay, I'll come to VIF later, but then yeah, so you all would have heard about that linear regression can be also be represented in forms of linear algebra, right? So in case where your beta coefficient is, this is the equation of beta coefficient, x transpose x inverse into x transpose of y, right? We'll come to this derivation in the upcoming slides, but as of now just think that this is how you get the beta value or beta coefficient, or the one x2 x3 and so on, right? Now you can you see what is the left kind of term here? X transpose x inverse, right? Correct. Now how do you calculate an inverse of a matrix? So now you see beta, if you want to calculate beta, you will have to calculate or do the calculation of a inverse calculation of a matrix, right? Now to do that inverse calculation, what is the formula? How do you calculate so the inverse of this matrix on the left hand side?
Remember dividing adjoint of a matrix by its determinant.
Yes, adjoint of a matrix by its determinant. Now determinant, what is the value? AD minus BC, right? Now, so this will give you the inverse. So basically in calculation of this portion, this whole thing will be used. Now imagine what will happen in case you have multicollinearity in this matrix. So you can imagine a matrix like this, 1, 2, and here it is 2 and 4. Okay, let's say your matrix values is this. Can you see, can you make this as a, can you do any kind of column transformation here? So that one column or row becomes 0, or column or row, any transformation?
Yes, C2 minus 2 C1.
Exactly. So I'll put that in C2, right? So C2 equals to C2 minus 2C1. Okay, I might not be right. So then, so C2 equals to C2 minus 2 of C1. So this will become 0, and this will also become 0. Can you calculate a matrix, a determinant of a matrix which has like 0 in one row?
It will be 0.
Yeah, exactly. Right. So now so this determinant will be 0. Value of determinant will be 0. When you feed that 0 in the denominator, what will happen? Can you calculate? Will you be able to calculate this inverse?
No, ma'am. So it will be 1 by 0, it will be infinity.
Exactly. So it is not calculable. So if you have multicollinearity, why? So C2 here, this is C1, right? C1, and this is C2. You had a dependency between C2 and C1. C2 is 2 times of C1, right? C2 is 2 of C1. You have a relation or dependency between these two variables, right? Sorry. Right? Now, this tells you that you have multicollinearity in your data, where one variable is somehow related to another variable. So when you will go for this kind of data, when you come to the calculation of calculating inverse, one or the other row or column will become 0, 0, and hence your determinant's value will become 0. When you will feed that 0 value in the formula of inverse, you'll not be able, that is not a calculable thing, right? So 1 by 0. So you'll not be able to calculate the inverse of that matrix. So no inverse, no beta, right? So in case of multicollinearity, this is the problem. Why multicollinear? Why do we have this assumption at all before we do any kind of linear regression problem, right? Because in case of multicollinearity, you will not be able to calculate determinant, hence no determinant, hence no inverse, hence no beta, hence no linear regression, right? Any questions here?
Ma'am, I have a question, but here in this case, as we have only like less data like 1, 2, 2, 4, so we can find a relationship like C2 equal to 2C1. But if we are dealing with like large data set, then we can't find the exact relationship between feature, right? Like C2 equal to C1, or in such way we can't find the relationship between feature.
Yeah, in that case, so yeah, you can still find, right? Basically, whether or not there is multicollinearity, you can detect it, right?
Yeah, we can detect it, but it will be only a less amount, right?
Less amount, right? Even if you have less amount of multicollinearity, right? In that case, what will happen? Again, the problem of that omitted variable bias will come. Here, let's see. Okay. In this equation, what we just went through.
Yes, ma'am. I got it, ma'am. I got it.
Yeah, you got it, right?
Yeah,
even if you have little dependency, then your coefficients itself will be not true reflections of what you wanted to achieve. You wanted to say how much change in X will represent how much change in Y. But here you got an influence from the other variable itself. So now X coefficient, that was B, no longer remains X true coefficient, right? It has influence from Y, Z, right? So that also is a problem, right? You will say, oh, yeah, so your coefficient is kind of inflated here, right? You see, instead of B, it is now B plus CF. Now you'll say, oh, X is like highly important for my model. But it was not. It was just B. Your multicollinearity kind of led to inflated coefficient, which made you think, oh, X is extremely important for my Y. Whereas in reality, that was not the case. That is just because of multicollinearity, you're getting a false view of that. Correct?
Yes, ma'am.
Okay, then this is the problem with multicollinearity. Why should we go ahead with assumption? Why this assumption is the most important assumption for linear regression? And right, so I've rarely seen, so we always go ahead whenever we get a business problem or a use case, right? We just go ahead and try applying that linear regression or sklearn model libraries, or stat model, right? I've rarely seen people like going ahead and checking those assumptions, right? And in fact, nobody teaches going ahead and going ahead and checking those assumptions, right? But right, what is this important? What is the importance now? And this also makes you interpret once you get an error, even if you had like strong multicollinearity and you get an error, so you will get a value. See this error. If you are able, one second. See, there are questions. The person tried to fit a linear model here. Now they got an error, linear algebra error, singular matrix. Right now, in order to like understand this error properly, also, even when you like blindly go ahead and just apply linear regression, right? You should be able to understand the concept behind the concepts, right? The exact same thing which I was talking in the start of the session, a workshop, basically, that you should be able to understand why are you getting this error, singular matrix error. This error comes when you have this kind of condition. You cannot calculate the determinant of the matrix, right? And in that case, you get this kind of error. If you try still forced to apply linear regression in a data where strong multicollinearity is present, right? And how do you measure this multicollinearity presence? How do you diagnose this multicollinearity, and how do you get rid of it? So ideally, practically, have you heard about VIF? Anybody? Can anybody tell me what is VIF and what does it do basically? Anyone put in the chat box? Wants to put in the chat box? Sorry. Okay. So variant, yeah, somebody was going.
I heard it, but in many times in the assumptions, but I don't know exactly how it works. But okay. I heard it in assumptions.
Good. So that is what I was saying. So you would have heard about all these assumptions, but how often do you try applying this? How often do you exactly try to understand what is the meaning or what is the reason behind these assumptions, right? So that, so VIF, going back to VIF, variance inflation factor. What does it do? The formula, okay, you can remember the formula, but anyways, it doesn't matter. Once you understand the concept, what it is doing, it will be way more easy to remember this formula. 1 upon 1 minus r square. But you see, in the variable, it is written as x1, not x. What VIF internally will do, it's a sequential process. First, it will calculate. So what internally it will do, it will also try to fit linear regression model. So it will try to detect multicollinearity. So multicollinearity means dependence between your independent variables. So it will try to fit a model between x. Let's say you had 3 variables only, right? 3 variables only in your model. Beta 1, beta, or let's say beta 2. Beta 3, maybe beta 2 is this one. Okay, so this x1 is equal to beta 2 x2 plus beta 3 x3, right? Okay, same way it will establish one more. Now it will try to fit a regression, taking x1 as the response variable and x2 and x3 as the independent variable, right? If it gets more r square in that equation, x1 equals to beta x1 plus beta 2 x3, what will it tell you? Like if you get more r square for that particular model? Anyone?
Ma'am, r square is like, is it goodness of fit here in this case?
Yes, goodness of fit. Let's say you have like x1 and it is actually dependent very well on x2, okay, and you are kind of regressing x1 in terms of as a function of x2 and x3. Now let's say there exists a strong multicollinearity, right? So this regression will give you good r square or a large value of r square, correct?
Yes, ma'am.
Any confusions in this statement? Anyone? Please feel free to ask. any confusions, any counter arguments also, if you have anything. Okay, so same way it will, now it is regressing with x1 with respect to x2, x3. Same, for this you will, it will get an R square, goodness of fit of model, right? R square. For now, now it will apply this formula. More the R square, that means more there is dependency between x1 or any other variables here independent, more will be the value of R square, because you are regressing x1 as the y variable here. Now 1 upon 1 minus R square, 1 upon 1 minus large value, right? This will come to a very large value, right? So, when R square of this this whole equation is large, VIF will be large. When R square of this equation is low, suppose there existed no multicollinearity between these two variables, right? X1 and X2 and X3 interpreted. Sorry. So X2, so this model would have given lesser R square, right? So in that case, it would have resulted in less value of VIF, right? So one by one, you keep on calculating this value of VIF, and one by one, you keep removing the variable one by one, right? So let's say in first it regressed x1 with respect to x2 and x3, it found more R square, more VIF, it will remove x1 because it is highly correlated with some of the other variables, right? Now next it will do, now what are the two variables left? X2 and x3. It will try to regress x2 with respect to x3, right? Some function of x3. Now lesser, if it finds again less value of R square, less value of VIF, it will take these two. Okay, x2 and x3 will be my final variables in the overall model, right? Independent. So this is how VIF internally works. That is why you keep removing sequentially VIF. Once you keep getting VIF, you keep removing sequentially the variables one by one. Now, there's no formal value as of now, but yeah, general market standard or the threshold that have come up with experiments, a lot of experiments, is like that if value X of VIF exceeds 10, then there is strong multicollinearity. But in right, so but lower the value, better is the model, or there is low multicollinearity basically. Okay, any questions? So because these are the most important factors. So multicollinearity, why it should not be present, what happens if multicollinearity exists, why are you not able to calculate determinant and inverse basically in case of multicollinearity, how do you test all these conditions and assumptions. I'll just take a pause over here before we move on to the next topic, OLS. How does OLS work? And just I'll just pause for some questions, some statements, any confusions you have.
Ma'am, while calculating variance inflation factor, so every time we will be taking one feature and we will be considering it as a dependent and every other feature as independent variables.
Yes.
Ma'am?
Yes.
So every time if we get a high value of VIF, we will remove that feature and we'll proceed.
Exactly. And this is all done using programs only. You just call that VIF function, and VIF will do nothing but internally it will do regression only between the independent variables themselves, one by one, taking each one of them once as a Y variable.
Yes.
Any questions? Any statements? Anything? Did you find this assumptions or going behind the concepts as useful, at least, or did you used to look at this aspect at all, previously while fitting linear regression algorithms? So did anyone try to establish this fact? Why are those assumptions before any model, before we try linear regression? Thanks Akash. Okay. Anyone, please feel free to talk, feel free to express yourself. Okay, how many of you already knew linear regression, or how many of you already studied linear regression earlier, and then you have fit linear regression in the past? And did you go ahead and check for any of these assumptions earlier? And even if you did, like, did you try to find out why this existence of this assumption, why does this assumption exist at all? Anybody try to find this reason, or like, did you try looking at linear regression from this view?
Ma'am, I have a doubt.
Mm-hmm.
Ma'am, the difference, I want to know that this difference between that multicollinearity and endogeneity.
Okay, endogeneity is basically, there should be no relation between the X variables and the errors, right? But the problem which it ultimately leads to, both of them, is like your true coefficients will, your coefficients will not be a true estimate of the reality. That is the problem. But I was giving this equation example to make that statement clear from here. So both endogeneity or multicollinearity can lead to this problem of omitted variable bias.
Okay, got it. Thank
you. Okay. Any questions, any doubts? You can express your thoughts. How do you like this session?
Yes, the assumptions we tried only about theoretically, but like haven't implemented it in code, man. We'll just load and we will be removing some unwanted feature and we'll be fitting the model.
Yes, that's what. So in fact, that is the most common practice that many people do. That's but yeah. And more importantly, why, even if you tried assumptions, right? Even if you tried verifying those assumptions, did you even try thinking why those assumptions exist at all? What is the problem? What if my data is not following those assumptions and still I fit linear regression model? Has anyone, like, there's no, because most of the people in data science or in this industry, not many people will not go ahead and check the causes of these assumptions, why these exist or why these exist, right? So that's what. So here at Algoritmo, we try to not only just go ahead and make you learn or make you understand what is linear regression, what does it do, when to use, right? So why the concept behind the concepts, right? The importance of a concept, the overall existence of a concept or an assumption. So at Algoritmo, we try to emphasize most on these background or underlying concepts, right? Okay. Any more questions before we move to OLS model? Ordinary least square model. You could share your feedback also. Okay. And definitely at the end of the session, we'll be sharing a feedback form. But anyways, feel free to express yourself here if you feel this workshop is, you want something more, or you want to ask some questions, you want to, you have something else in your mind that you would like us to share with you, right? Okay, we'll move next to the OLS, ordinary least square regression. So this is one. So as I told earlier, there will be multiple techniques that exist for linear regression, like stochastic gradient descent, kernel gradient descent, OLS, least square, right? Sorry, but OLS or ordinary least square is one of the most commonly used and that guarantees you the least square estimators, right? The beta coefficients we call as estimators, right? So how does it work? It has a cost function that it requires to minimize. Cost function as in any kind of minimization algorithm or maximization algorithm. So this is a minimization algorithm, right? It tries to minimize the error, right? Hence, minimization algorithm. How does it try to minimize the error? Basically, it will try to give you the best fit or see, there will be multiple possible lines. So to see the gray points here represent the true data. You will obviously, you can draw hundreds and thousands of lines that will like revolve, or that can describe, or that can be the model for you, the linear regression model. But among those 1,000 lines, how to identify the best line here that will give you the minimum error, right? The least error. That is the work of OLS. It tries out of these 100,000 lines, it will try to just minimize the error in such a way that you get the best possible line here, right? So minimization algorithm, it works on minimization, ordinary least square. Least squares represent your coefficients of the independent variables like beta 1, beta 2, beta 3, right? In an equation of y equals to beta 1 x beta naught plus beta 1 x1 plus beta 2 x2 and so on, right? And it will find a line, an optimal line, right? It will not just be close to one particular point. It will try to find a line that is optimal, right? The optimal is the best for us, right? Because you cannot, obviously, linear means linear. You don't have a line, you cannot have a line that can pass through all these random points, correct? Using OLS, you will, because you have a line, you will have to have something straight, right? Y equals to mx plus c, that equation. So obviously it will have some errors, but the ultimate aim is to minimize those errors as much as possible. Best linear estimator. Hence the term comes from like blue, best linear unbiased estimators. Now these best line should also be in such a way that you not only minimize the algorithm, but let's say you are building, you have these kind of data now. Now, again, when more data comes in, again, in that case also this line should be the best fit, right? You cannot retrain your model every time the new data comes in, right? As I told you earlier, this model you can prepare once and you can literally get rid of these points, and then only this line or only equation of this line represents your OLS or the linear regression model. Whenever one new x comes, you will fit that x value into the equation of y equals to mx plus c, and then you'll get the corresponding value of y, right? And yeah, slope is the coefficient. Slope meaning in the equation y equals to mx plus c, m represents the slope and also represents the effect of that x variable on the y, or the true coefficient of x is represented by m. And in case you have an intercept, right? So y equals to beta naught plus mx. So that beta naught is how much away from the origin you are there, right? Okay. Now, what is the cost function here? The error term. Error term in terms of matrix is y minus xp. So because you know, right? So y equals to mx plus b plus error, right? Mx plus error, and obviously you will have one beta naught or the intercept term also. You might or might not have, but yeah, I'll just keep it as of now. So now, what is the errors value? You just take the mx on this side of the equation. So y minus mx becomes your error. Y minus x beta naught or xm, whatever you want to denote this m term or the slope of the line by whatever term. So as of now, we'll just treat it as beta naught, or sorry, beta. So y minus xb and sum of squared of error. So y minus xb whole square. In terms of when you do it in terms of linear algebra, so it will be y minus xb transpose into y minus xb. Like in terms of matrix, this will be the equation of the error. Okay. And in terms of normal calculus, it will be like actual yi minus predicted yi So yi bar whole square, right? And summation, obviously summation of I equals to 1 to n. So this will be in terms of calculus, and this will be in terms of matrix, y minus xb transpose into y minus xb. Okay. Any confusions in the working or the functionality of OLS till now? Any questions? Share your thoughts. Feel free to share your thoughts as well. Like if you are finding anything difficult or finding anything surprising, anything.
No questions, ma'am.
So method of this OLS and the curve fitting is same.
Curve fitting, yes, it fits a curve. Basically, this is also a curve fitting, right? In this case, your curve itself is a line as such. It's not a curve, but you are actually trying to fit an equation here, right?
Okay. So in case of, if it is a polynomial regression, we can say it is a curve.
Yes. In case of polynomial regression, it will not be a straight line anymore. You will have y equals to beta x plus beta 1x square plus beta 2x cube, something like that. So it will go ahead with, in that case, it will be like more specific or more close to these points. X square might be like this graph and like this, and cubic or more graphs more terms, squares or cubic or raised to the power 4, anything you can draw, but that will lead to overfitting, right? You are making your model very specific to the data you have in your hand. But remember, that is a sample. What is your ultimate aim? Ultimate aim is that tomorrow, whenever unseen data comes, your model should be generic enough to capture the pattern in the unseen data. If you will make very specific cubic or like a polynomial model, like very specific, very specific to the data in your hand, then you will perform worse in case of unseen data. Because now unseen data point might be falling here, right? Unseen data point might be falling here. But because you made a very specific model to your training data, always this error will be high. See, but in case of linear regression, let's say you tried just this line, right? See, the error here is less as compared to this curve, right? Devansh, did I clear your doubt?
Yes, ma'am. Thank you.
Any more questions? Okay. I'll just, because we have less time with us, I'll just quickly try to move to the next part. So basically, it can be, as I told earlier, OLS can be interpreted in the form of calculus or the matrix form also. So anyway, whatever form it is, always your aim is to minimize the error, which is actual minus forecast whole square, summation of I equals to 1 to n, right? Now, what happens in calculus if in case of any kind of minimization or maximization? What do you do? Anyone? Have you heard about differentiation? What do you do in case of if you want to minimize or maximize any kind of any term or any equation, any function basically?
And we differentiate the function with respect to the constants, variables, and then solve the equation, and then find the second derivative of the function and put that value in the second derivative. And if we will get a negative, then we say that the function is maximum at that point, and if we get a positive, then we say that function is minimum.
Yes. So basically, yes, you do. You are exactly correct. So you don't. So basically, you differentiate it once and then equate it to 0 itself at the first differentiation. But this is how you will calculate any minimization or maximization, or you'll solve for any minimization or maximization algorithm, right? You calculate the derivative of this function with respect to what you are trying to minimize, the variable, right? So the beta naught and beta 1. Remember, in this, we are trying to find the optimal values of beta naught and beta 1, right? The slope and the intercept. You're trying to, because only if you get beta naught and beta 1, you'll be able to get the equation of your line, or basically the end result of your linear regression model. Now, if you try to divide, take the differentiation and equate it to 0, you will get the optimal value of that parameter. Now, one more important tweak here. Here there are two variables to be whose minima we want to calculate, correct? Now, in case of two variables, what we used to do in calculation? Calculus, sorry. Anyone remember? Partial differentiation. Anybody has heard about partial differentiation?
Yes, ma'am. Like partially differentiation, we'll be doing it with respect to each one, and we'll be
exactly
equating it to 0.
Yes, yes. So here also, we will be partially differentiating this equation once in terms of beta naught and once in terms of beta 1. So when we do partial differentiation for beta naught, then b1 remains constant and the vice versa, right? So if you equate, if you take a derivative, so f x square, so 2x it will become. And since already you have right hand side, you have 0, so 2 will go that side and it will become 0. So you'll have summation of yi minus summation of beta naught minus summation of beta 1 xi. Now, since you are differentiating with respect to beta naught, minus 1 will also come outside. It will go to the right hand side and will become 0. Again, you'll have this term, and then beta naught, summation of I equals to 1 to beta naught. Since beta naught is like a constant variable, right? Intercept, a number, right? So summation of I equals to 1 to n of beta naught is nothing but n beta naught, right? You are basically taking n times the beta naught, right? So basically, you will try to differentiate it first in terms of beta naught, second in terms of beta beta 1, right? But beta 1, when you will try to differentiate it with respect to beta 1, you have an xi attached with that. So that xi will also come outside, right? So ultimately, when you keep solving for this, right, so you will get these values. So yi bar minus xi y bar, sorry, x bar for beta naught, and this equation for beta 1, right? Now, from first equation, you take the value of beta naught and put it into the second equation. So then you'll finally get the beta 1 equation in terms of x and y. And x and y you will already have in your data, right? X and y values, historical data, independent and dependent variable values, you will already have with you, right? So then that you insert that values in this equation of beta 1, second equation, you will get the exact value of minimal beta 1. What should be your ideal estimate of beta 1? And then again, once you get the beta 1, again you feed back the beta 1 back into the first equation to get value of beta naught. It's just like substitution of one value into the other equation, right? Since these are two variables and we have only two equations, so we'll have to go ahead with the partial differentiation. So what does it mean by partial differentiation? First, differentiate with respect to beta naught, equate it to 0, get the value of beta naught in terms of x and y, obviously. And then again, differentiate beta 1 with respect to, again, differentiate this cost function with respect to beta 1. Feed the values of beta naught from equation 1 to equation 2, and then get a value for beta 1 in terms of xy, right? And then you can put the values from your data in x and like x and y you'll already have, right? And you can feed these values here and you can get the value of beta naught and beta 1 for your data. When it comes to
how the algorithm will know where to stop? Like it will be based on the loss, cost function.
Yes, that's what. So it will be basis the loss function. So it will. So in terms of beta 1 and beta naught, right? So you will have something like this curvature, minima, local minima, global minima it will try to find, let's say, right? So when you there is a scope of, so if you are here, there is a scope of further going down, right? When you cannot, so local minima itself, it is not stopping this at this point itself. The condition for this point is that your partial the differentiation should become equal to 0 here, right? You should no longer be able to differentiate, differentiate any further. So this is the condition that we are solving only for this point. But in stochastic gradient and other methods, right, you can go ahead and look at the various kind of algorithms and all at our Instagram channel or Instagram page or LinkedIn. Algoritmo, right? So how does stochastic gradient work? How does other algorithm? So there it is a sequential process. Basically, it tries to come here and then it tries to see, again identifies, whether sees the cost function. Sorry, it tries to minimize the cost function and then gets an estimate. Again, tries to fit the model and it keeps on going until it reaches this point, this global minima, right? But that is as per gradient calculation, and it keeps on updating parameters. Here we are solving for this particular point where, so the condition for this point itself, the minima is that we should have the first differentiation as 0.
This graph will also have, I think, like, will it have any another axis about like one axis is loss, under two axis is beta naught and beta 1?
Yeah, no, that we are solving separately, right? So one second. So we are solving separately as in, y-axis will be loss, x-axis will be beta. First time it will be beta naught, and this will be again the cost function, the error basically, right? Error. Now again, the second time you are solving it is for beta naught, right?
Okay, we will be solving it individually.
Individually only, but partial differentiation. So there will be effect of this. Individually only, right? Two equations. So this equation for this one, the second one for this one.
And so we will be doing this for every sample, every data point.
I didn't get you. So yes. You are what you are trying to. If I understand your question, this will be applicable for all the entire data points you are saying, right?
Yes, ma'am.
Yes. Okay. Any questions? More questions? Any thoughts? Comments? Anything anyone would like to share? Anybody? Like, now you know, right, how we get this values of beta coefficients, intercept and the coefficients of each variable. We have taken an example of just one variable or simple linear regression here, beta naught and 1 beta 1. But the same way you will keep on getting this beta 2, beta 3, beta 4 for each of the variable. And you do this as a variable, right? Because you have this summation here, summation of beta naught or summation, right? Summation of xi. So for each variable, you will do this. Okay, I'll go to the next slide considering the time we have. Yes.
Sorry, like if this is something beyond the scope of this session. So like I was trying to connect that graph with respect to neural network. Like there will be having the loss with respect to each epoch, the loss will be reducing. So, but in this case, we'll be having only one epoch, right? Like, is it like one epoch?
Yes, because this is, here you don't have, you can try multiple iterations, but this is like, it's very different from the deep learning where you have multiple iterations right there. And you, at each iteration, you keep on doing that minimization and then update your weights accordingly, right? So that's why, that's why you have like at each step, there is a forward propagation and then backward propagation, right? So basically you forward propagation, you take your differentiation and all those things, you carry on to the next layer, and then back propagation, you basically update your weights with basis the results what you got, right? For the gradient.
So there we will be doing that minimization after every epoch. So here we'll be doing it after every sample. Is it like that?
So basically this happens for an entire variable here itself, because there is a summation, right? You can see. So for entire variable, you will do over this one.
Well, like,
this is like a one sample at a time. One sample as in one variable at a time, kind of. For each variable, you will do this.
Yes, so all every, for every data point.
Not for every, summation, right? Summation.
Yes, ma'am. Okay. So we'll be having only one epoch, right? Here in this case, like only one iteration.
Yes. If there is actually no epoch, but you can, if you want to relate it with data, deep learning, yeah, you can treat it as one epoch here as of now.
Yes, ma'am. Okay, ma'am. Thank you.
Yeah. Least square, yes. We already talked about this. So beta, or in terms of matrix notation, you can represent it with x transpose of x raised to power -1. Basically, that means inverse, right? So x transpose x inverse into x transpose of y. This is the equation of beta coefficient, right? Now we already saw earlier that in order to estimate beta, you need to have an inverse. You should be able to calculate an inverse. For calculating inverse, you should be able to get the value of a determinant, right? And in order for a determinant to exist, you should have no multicollinearity in your data, right? And in terms of matrix notation, error transpose error. So square of error. So what is the square of a matrix, right? So transpose of that matrix into that matrix itself, right? So that is how sum of squared error will be in the matrix notation here. In matrix notation, you can simply represent these parameters or beta naught, beta 1, like a matrix like this. So, right? So y will be only one dimensional, right? So one meaning, so y1, y2, y3, y4. For each row of x1, you'll have one y1. Now, why we have added 1 here? Because we need to, so beta naught plus beta 1, right? Beta naught is a constant. For that constant, we have added here 1, 1, 1, 1 in the x matrix, right? x11, x12, x13 are all like two 3-dimensional data, right? x1, first rows, first variables, first record, first variable, second record, and so on, right? Error are error 1, error 2, error 3. So for each y, you will get one error. So whatever is the dimension of your y matrix, the same dimension will be there for the error matrix. So y1 equals to beta naught plus beta 1 x11 plus epsilon 1. If you simply multiply this, so beta 1 into x1. So this M matrix into X matrix, this will give you this term beta naught plus beta 1 x1 and plus error 1, right? So this is how matrix notation looks like for regression. And you are solving this for, again, calculation of beta 1, beta 2, beta 3. So this M matrix or this slope is what you are interested to solve for. Okay. It's always easier to understand, mostly like if they're expressed in matrix notation, right? It's convenient. You guys got the concept of multicollinearity from this one, right? Why shouldn't we have multicollinearity? From the matrix notation, it's very easy to understand or derive some inferences out of anything, right? So next one is like sum of square total. So what is decomposition variability? Is nothing but how good is your fitness model? What is the goodness of fit of your model? How well does it explain the variability in the data, right? So there will be some characteristics of data, right? Like sample mean, variance, standard deviation. How well is your model able to estimate that? Correct. So this and all are like sum of square total, sum of square regression, sum of square error, R square, adjusted R square. These are all the metrics that can help us to do that, right? To estimate, to establish the fact that how close is my model or how close my sample can mimic the characteristics of a population, right? So that is given by these kind of metrics, Sum of squared total is y minus y bar, actual minus mean of that variable, right? It is just like assuming you don't have any model. So what will you say? Oh, my average prediction. What if I want to predict for any further future? What will I say? Okay, take the mean, and that mean only I'll say, okay, I'll keep it as my forecast or prediction, right? For any future data, right? So in case of any absence of any model, right, any mathematical model, any other model for that matter, so in that case you simply go ahead and replace your forecast or predictions with mean of that value. So sum of squared total is y minus y bar, right? So y bar is the mean line, mean of that variable. Y is something which you predict. So y actual point is this gray point. Y minus y bar represents sum of square total, right? It's also kind of like mean is also considered as having as a baseline model, right? Just you're saying that all my forecast will just be like mean of what I'm getting as of now of that variable, right? The response variable. Formula again, as I told, y minus y bar. So let's say imagine this y, the red line or brown line represents basically the y bar, and your blue lines represent your actual data. And so in case, see, there is no linear model here. There is no, I don't have any linear model in this case. So my SST will be y minus y bar whole square. In case I would have had a model like this, right? So then comes new dynamics, right? Now you have one more model here. You designed a linear regression model in order to estimate this. You no longer are saying that my mean only is my model. No, now your mean is not the model, right? So in that case, one second. Yeah. In that case, you will have other terms called as SSR. Now, SSR is sum of squared regression. So now see this black line. You have designed a model now. So now what is SSR? Your model, how much it is able to capture the variance, or how erroneous is this as compared to the actual points. So y actual minus y predicted whole square. That represents your SSR. If you see the formula, SSR. Actual minus predicted. Sorry, I'm so sorry. That is sum of squared error. What sum of squared regression is, you compare your model with the mean, how much your forecasted or predicted values, are they good? Are they better than mean value when you were just estimating y variable using your mean of the y variable? So SSR is like when you have the model, when you have a linear regression model, something like this sort, right? And SST, so when you predicted y predicted minus mean of the y variable. So this is what this will give you the SS regression, SS sum of squared regression, right? Now the sum of squared error, it will give you actual minus predicted. Actual minus predicted. How close is the model with respect to actual and predicted? So if I want to like go ahead and tell you the relation between all these terms, SST equals to SSR plus SSE. Total variance equals to explained variance plus unexplained variance. Unexplained variance is error, right? Unexplained variance is error. Yeah. Unexplained variance is that error, SSE. Explained variance is SSR. SST is total variance. Now, if you see this diagram, right, it's a very good representation of the relation between SST, SSE, and SSR. SST, so in this case, you have a baseline model, which is nothing but the mean of the y variable. You have your own linear regression model, which gives you the y bar, right? And you also have a actual point. This green point is the actual point, right? Now, see this one. SSE will be, what is your actual minus forecasted. Forecasted for this point is the value at this line. So this is SSE. This is SSE. You can see from here till here. Now What is SSR? For SSR, you see y predicted minus y average. How much my model is, how well it is it better than mean or it is worse than mean? So SSR is what you predicted for this line, this point, versus what my mean was. So y pred minus y bar. This is SSR. Okay, and total is obviously actual minus the mean. So actual minus the mean is total variance, right? R squared, as you all know, as we already talked about it, if there are metrics to evaluate these models like R square, it all depends on these values only, what we were talking about. So goodness of fit. So variability metrics like SST, SSR, SSE. So 1 minus SSE divided by SST. So how much of the variance is explained by your model versus the total variability in the model or the data? How much is the variance explained by your model versus the total variance, right? That is given by R square. Now, one challenge with R square is you will, whenever as you keep on increasing the variables, right? Like let's say you had 15 variables, you took first one variable, then it increased, then second variable, then it will further increase. And as you keep on taking more and more variables, R square will always increase, right? Because there will be some error and SSE will be shorter, SST, this whole equation will give you some value, right? Now, but ideally we should be doing some subset selection, right? We should not be like taking every variable. Might be that one more variable is not important, not adding enough value to our model. So in such cases, we should penalize the model, right? That is done by adjusted R square. So the formula here, this one, the second one, it represents adjusted R square, R bar, right? So what is this formula? 1 minus 1 minus R square, n minus 1 divided by n minus k minus 1. K represents the number of features. K is in denominator. Now, whenever you add extra variable, right, it kind of penalizes the whole R square. Your R square value itself gets penalizes because it's in denominator. More the number of variables you add, more the penalty you will get. And n is the number of records in your model, right? Number of records, number of observations, whatever you call it. So R square in a view is basically the correlation between the actual and predicted value. But yeah, obviously R square keeps increasing as you have include more and more variables. So to penalize that, we have something called as adjusted R square. In that adjusted R square, K, meaning the number of features, is in the denominator. So that kind of penalizes whenever you add a variable, and that doesn't add enough information or enough variability to our model, right? That is the adjusted R square. What is a good R squared value? Closer to the 1, it ranges from 0 to 1, right? So closer to 1, greater, better value, better model, right? Good model. Closer to 0, not very good model, right? Same is the case with adjusted R square. Because so when will you have absolute perfect value of 1, best model? When we have no error, right? Practically it is impossible, but yeah, when you'll have practically 0 error, then you'll have an R square of 1, correct? When you will have R square of 1, that means there's no error. R square of 0, meaning you are doing your model is not doing anything extra, right? You can simply replace your model with the y bar or the mean of that variable, the response variable. Even that will give you R square 0, right? So why do you need an have that? So when your model